All right, welcome. Today, we're going on a quest for something that sounds simple but is incredibly powerful: certainty. We're diving deep into the foundations of logic and computer science to tackle a concept that's holding up everything from pure math to the apps running on your phone.
So picture this. You're trying to solve a really complex problem, right? And you're breaking it down step by step, making it simpler. But what if one of those steps sent you down a path that just never ended? What if you got caught in a loop, forever simplifying, but never actually reaching an answer? That's the fundamental nightmare we're going to talk about today.
So, our journey really begins with this deep human need for simplicity. You can think of it like tidying up a super messy room. In logic, a proof can be just as cluttered, and the first big goal is to clear away all the junk and find that clean, essential core. Now, what's so cool about this is that logicians believe that every proof, no matter how tangled and complicated it looks, has a perfectly simple form hiding inside it. It's kind of like how a complex math equation can be boiled down to something elegant. The real trick, the whole game, is just figuring out how to get there. And that whole process of tidying up, it has a name: normalization. This is the formal method for cleaning up that messy proof. You go in, you find all the unnecessary steps, these little logical detours, and you just start removing them, one by one, until all you have left is the most direct, straightforward argument possible. Okay, so normalization helps us simplify. Great, but this opens up a huge can of worms, which brings us to the real hero of our story today: strong normalization. This is where we get the ultimate guarantee that our simplification process won't completely fall apart. Just think about it for a second. When you're cleaning up a proof, you often have choices, right? You could simplify this part first, or maybe that part over there. But what if making the wrong choice leads you into one of those terrifying infinite loops we just mentioned? I mean, that's a massive risk, especially in really complex systems. And this is exactly where strong normalization steps in. It's not just a weak promise that some path to a simple answer exists. Oh no. It's this incredibly powerful, almost magical guarantee that every single path you could possibly choose, no matter how weird your choices are, will absolutely, positively lead you to that final, simple form. So let's just boil this down. Normalization basically says, hey, there's a path through this maze. Good luck finding it. But strong normalization, it says, don't even worry about it. Every single path you take will get you to the exit. No dead ends, no going in circles. It's the ultimate safety net. Now, you can imagine proving such a powerful guarantee is not easy, and it gets especially tough when you try to apply it in one of the most complex arenas out there: the world of classical logic. This is the big leagues, where this idea gets put to the ultimate test. The specific system we're talking about is a bit of a mouthful. It's called second-order classical natural deduction. So let's break that down real quick. Natural deduction just means it's trying to copy how we humans actually reason. Classical means it uses powerful rules like proof by contradiction. And that second-order part, well, that's what makes things really interesting and really tricky. So why is this system such a beast to tame? Well, for starters, it's trying to mimic our intuition. And let's be honest, human intuition can be pretty messy. Second, that second-order bit means it can talk about the properties of things, not just the things themselves. That adds a crazy amount of power and complexity. And finally, the way it handles concepts like negation can create these really tangled, tricky logical knots. So how on earth do logicians do it? How do they prove that in a system this wild, every single path is safe? Well, it all comes down to a really clear mechanical process for taming these potentially endless simplifications. It really just boils down to a few steps you can repeat. First, you hunt for a detour. That's a spot where you introduce an idea and then immediately get rid of it. Totally redundant, so you snip that out. Then you look for other rules that are just in a clumsy, inefficient order. They call these permutative conversions, and you reshuffle them to be more direct. And you just keep doing that over and over until the proof is as clean and direct as it can possibly get. Now, to actually prove that this process always works, researchers come at it from all sorts of angles, using some seriously sophisticated tools. Some use these algebraic systems like the Lambda Mu Calculus, which is kind of like a programming language for proofs. Others use graphical things like proof nets, which turn proof into diagrams you can analyze. These are all just different weapons in the big fight for logical certainty. Okay, so at this point, you might be thinking,
this is kind of neat, but it's super abstract. Why should I care? Well, it turns out that this abstract idea has everything to do with the technology that we all depend on every single day. And this leads us to one of the most beautiful and frankly mind-blowing ideas in all of science, the Curry-Howard correspondence. It says that a logical proof and a computer program are basically the same thing. They're two sides of the same coin. A proof is a program. And once you let that sink in, it changes everything. So if a proof is a program, then simplifying a proof is the same thing as running that program. And if you can prove strong normalization for a logical system, that means you can guarantee that any program written in that system will always finish and won't get stuck in a loop. In other words, strong normalization is how we build trust into our computers. So what does this actually get us in the real world? Well, first, it proves the logic itself is solid and won't contradict itself. Huge. Second, it guarantees our programs will actually terminate. They'll finish the job. And most importantly, it gives us a foundation for building software for things like airplanes or medical equipment, systems where failure is not an option. We can prove that software is reliable and safe.
So this whole quest for strong normalization is really a quest for certainty in a really complex world. It's about proving that even in our most powerful and complicated systems, we can guarantee order and we can always find an answer. Which leaves us with a pretty big question for the future. If we can build this level of trust right into the logic itself, what's the next frontier for making our technology truly trustworthy?